All right, we hear the term machine learning thrown around all the time, right? And honestly, it can sound like, I don't know, digital magic. But what if it's less like a magic wand and more like a really powerful, really cool toolkit? Well, that's what we're going to do today. We're opening up that toolkit to see exactly how machines learn.
Yeah, I mean, that's the big question, right? We say a machine learns to spot a cat in a photo or predict the stock market, but what is actually going on under the hood? How does that even work?
Well, here's the secret. It's not magic, and it's definitely not one single mysterious thing. Machine learning is really just a collection of different tools. We call them algorithms, and each one is built for a very specific job. You got to think of it like a master craftsperson's toolbox. So for the next few minutes, let's pop it open and take a look inside.
Okay, first up in our toolkit, we've got the sorters. Their main job is something called classification, and it's pretty much what it sounds like. It's all about teaching a machine to take a piece of data and just give it a label, to put it into a specific category that we already know.
Now, this whole sorting thing usually comes in two main flavors. You've got binary classification, which is basically a simple yes or no question. Is this email spam or not? Will this customer buy the thing? Simple. Then you've got multi-class classification. That's where the machine has to pick from a bunch of different options, like, okay, what animal's in this picture? A cat? A dog? A giraffe?
So, how does one of these sorters actually work? Let's grab a classic tool from the kit, K-nearest neighbor, or KNN for short. It's actually called a lazy learning algorithm, which is kind of funny because it barely does any work up front. See, when it gets a new piece of data without a label, it just looks around at its closest neighbors. The K is just how many neighbors you tell it to check, and it basically takes a vote. Whichever category most of its neighbors are in, that's the category it gets assigned to. It's like a digital version of birds of a feather flock together, and you'd be surprised how well it works.
All right, let's slide open the next drawer in our toolkit. In here, we have the groupers, and their job is something called clustering. Now, this is where things get really interesting, because with clustering, we're not giving the machine any labels to start with. Nope, we're asking it to find the hidden patterns all by itself.
And that's the whole point, right? That's the crucial question here. Sorting is great, but what if you don't actually know the categories ahead of time? What if you have this giant pile of customer data, but you have no idea what your customer segments even are? You can't use a sorter because you don't have the labels. You need a tool that can discover the groups for you.
And that is exactly where a tool like K-means clustering comes in. This thing is a total superstar when it comes to grouping. You just have to tell it one thing, how many clusters you're looking for. That's the K. Then you just let it go to work and it automatically starts grouping similar data points together by finding the center or the average point of each little group.
And the way it does it is actually so simple and so clever. First, the algorithm just drops a few random center points, we call them centroids, right into your data. Then, step 2, it assigns every single data point to whichever centroid is closest. Now you've got some rough clusters. So for step 3, it just moves each centroid to the new average position of all the points in its cluster. And then it just does it again and again. Assign and move, over and over, until the groups don't change anymore. It's this beautiful way of just letting the hidden structure in the data reveal itself.
Okay, time for the next drawer in the toolkit. In this one, we've got our forecasters and our simplifiers. These tools are all about two things: predicting actual numbers and taking super complex data and just cutting through all the noise.
So the main forecasting tool we've got is called regression. So remember how classification was about predicting a label, like spam or not spam? Well, regression is all about predicting a continuous number. Think about trying to predict the price of a house based on its size, or forecasting the temperature for next Tuesday. It's all about finding that underlying trend, that line of best fit that's hiding in the data.
And then we have our simplifier, Principal Component Analysis, or PCA. Now imagine you have a data set with hundreds, maybe even thousands of different features or variables. It's too much noise. PCA is this fantastic tool for boiling all of that down to just the essentials. It finds a way to combine variables to create new ones. These are the principal components that capture the most important information. It lets you slice right through the noise without losing the signal. Super useful.
Okay, now we're going to switch gears completely and look at a totally different way for machines to learn. This isn't about data that already has labels, and it's not about finding groups. This is about learning by doing. It's learning from the consequences of your actions through pure trial, error, and rewards. The absolute best way to think about reinforcement learning is it's like training a pet, right? You don't give your dog a textbook on how to sit.
You give it a command, and when it does the right thing, you give it a treat, a reward. A machine learns in almost the exact same way, through this system of positive and negative feedback.
Now, this whole process has a few key players. First, you've got the agent. That's our learner, our little robot. The agent exists inside an environment, so in this case, the maze itself. The agent can take certain actions, move left, move right, go forward, and for every single action it takes, it gets a reward, which is just feedback from the environment. The agent's one and only goal is to figure out the sequence of actions that gets it the biggest possible reward in the long run.
But this whole setup creates this classic dilemma. Does the agent exploit what it already knows works to get a pretty good, guaranteed reward? Or does it explore? Does it try something new, something risky that might lead to an even bigger reward later on? Finding that perfect balance between sticking with what works and trying new things, that's the fundamental challenge of reinforcement learning.
All right, for our last stop, we're going to look at what is honestly one of the most powerful ideas in this entire toolkit, the idea of making different models work together as a team. This is called ensembling.
There's this great line from the source material that just perfectly sums up why we do this. It asks, why put all your predictive eggs in one machine learning basket? And that's it right there. Any single model, no matter how good it is going to have blind spots. It's going to make mistakes. But what happens if you combine the opinions of a whole bunch of different models?
To really get this, let's look at a single model first, the decision tree. These are super intuitive. A decision tree is basically just a flowchart of yes or no questions that sorts the data down a path. They're really easy to understand, but they have one critical weakness.
So while it's great that they're easy to follow, decision trees are really susceptible to a problem called overfitting. What that means is they learn the training data too well. They learn every little quirk and all the noise in the data they were trained on. And because of that, they completely fail when they see new, unfamiliar data. Basically, they memorize the answers instead of learning how to generalize.
So that brings us to the obvious question, right? If this single tool, this decision tree, is flawed, how do we fix it? How do we get all the power of a decision tree without that huge risk of overfitting?
And the answer is just brilliant. We don't use one tree. We use a whole forest of them. A random forest algorithm builds hundreds of slightly different decision trees, each one trained on a random little piece of the data. And then it just averages all of their predictions together. It's like asking a huge panel of experts instead of just one. By combining all those different perspectives, it cancels out the individual mistakes and creates a model that is way more robust and way more accurate.
And just how much better is it? The source material had this fantastic example. They took 25 different classifiers that were honestly just okay. They each had an error rate of about 35%. But when they combined them into an ensemble, the error rate of the whole group plummeted to just 6%. That is almost a 6-fold improvement in performance just by making them work as a team. That right there is the power of the ensemble.
So there you have it, a quick tour of the machine learning toolkit. We've seen the sorters that help us label our world, the groupers that find those hidden patterns, and even agents that learn from pure trial and error. You see, it's not a bunch of magic spells. These are logical, powerful tools. And the only question left is, now that you've had a peek inside the box, what kind of problems would you want to solve with it? Thanks for tuning in.